We are the FSAE Accumulator team consisting of Katie Bezjan, Kobe Carlson, Gabe Cohen, Jeremiah Grill, Cade Lansford, and Noah LeBaron. And just as a brief refresher on our project, we've been working to redesign the accumulator container for the Formula U Racing EV race car. Formula U Racing is an engineering club that competes in FSAE racing events with an electric EV or an electric Formula car every year. The accumulator container is a rules-regulated structure that contains all of the high-voltage segments and control electronics that are critical for the car's operation. The Tractive team is a sub-team on Formula U Racing, and they are our primary users as they are responsible for the design and upkeep of the car's high-voltage systems. The previous design of the accumulator container has had numerous problems. The container was never designed with cooling the segments in mind, so the cooling capabilities are entirely unknown. The internal layout had very poor accessibility of the important internal components. And finally, there were several safety issues like high voltage connections that were exposed and sharp edges. As a senior design team, we set out to solve some of these problems. So we began our design process by defining our objectives and metrics for the container design. Several of our objectives came directly from the 2020 FSAE rules. Two such objectives are keeping the surface temperature of every individual battery segment below 60 degrees Celsius. Each cell is equipped with a thermocouple, and any cell exceeding 60 degrees Celsius will automatically result in the car shutting off. We also had to ensure that our container could withstand 40 Gs of acceleration in a lateral direction and 20 Gs in the vertical directions. So after looking at the FSAE requirements, we moved on to some more objectives that would make the container safer and more user-friendly for Tractive Team. We wanted to provide them with easier access to the high voltage electronics, and we also wanted to reduce the size of each segment, which would make the container lighter and easier to handle inside of the chassis. We will do this by minimizing the space between each battery within the segments. As seen on our poster, figures 1 and 2 show our final CAD model of our design. Our team created multiple models and physical tests in order to ensure that this design met all of our objectives, and we are happy to report that this design did meet all of our criteria. Next, we'll briefly explain the methodology used in our CFD modeling.
Okay, so basically what we did is we used SolidWorks to create a CFD model of the battery segment. Basically simple steady state system, velocity inlet, pressure outlet, and we ran a parametric study where we iterated over various geometric spacings. But in order to prove that our CFD was accurate, we had to validate this with some sort of physical prototype. So we designed a thermal prototype, and that was our method of validation.
Right. And like Gabe mentioned, the goal of this was to replicate our segment basically as closely as possible so that we could physically test the segment and validate those CFD results. So to do this, we use 40 steel conduit segments to represent batteries. We then arrange these in a staggered configuration that's similar to our actual segment design. And we place these segments between polystyrene foam to hold and insulate them. The top and bottom of this was also sealed so that air could only enter through the exhaust and intake holes. We then also attached a fan to the segment. In an earlier version of our prototype, used a fan that was rated at lower CFMs, and both the exhaust and intake holes were smaller. But due to poor cooling, we actually ended up enlarging the holes and using a better fan that had higher CFM. And then also finally within the segment, we placed a resistor that was rated at high wattage, and we put one in each of the segments. So that way when we connected it to power, it would produce a heat source. And the resistors were all wired in parallel, but on two separate circuits. So there was 20 resistors in each circuit. And we utilized 2 power sources and adjusted so that each resistor produced 2 watts of power, or 2 watts of heat and power, which is approximately what our batteries will do in actual segment. And our final model can be seen in figure 3 on that poster. And once we had built this, we connected 3 thermocouples to each battery segment, or throughout the battery segment. And we connected the resistors and fan to power at the same time and started recording the temperatures, basically starting from room temperature. And we use these temperatures to then compare it to our CFD and validate those results.
As Kobe mentioned, the FSAE rulebook dictates that the accumulator container will be designed to meet strength requirements that predict the container will safely contain the accumulator segments in the event of a high-speed crash. The container must be able to withstand 40 G acceleration of the 6 accumulator segments in the forward and lateral direction, and a 20 G acceleration of the segments in the up and down directions. To balance the strength of the container against the removal of material to provide for ventilation and wire routing, we created a dynamic explicit finite element model in Abacus and used the model to iterate our design in conjunction with the CFD model. The container is made from a material model that allows for finite element deletion so that we can see when, where, and how the container is failing. Fixed displacements and rotation boundary conditions were created at the mounting holes on the base flange where the container is fixed to the chassis. The accumulator segments are modeled as elastic polycarbonate prisms and given surface tractions to accelerate in the desired directions. After running the simulations, we observed max stresses and displacements throughout the container.
Once we turned on the fan in our thermal prototype, we waited for the surface temperature of the conduits to reach a steady state temperature. And we did this by monitoring the thermocouple readings in real time. Afterwards, like Cade said, we created a CFD model of the thermal prototype and compared the steady state temperatures from the thermocouples to the nodal temperatures at the same cell location in our CFD model. We found that the percent error values between the thermocouple readings and the CFD nodal temperatures was reasonably small for thermocouples 2 and 3, but the percent error was much larger for thermocouple 1, and that's listed in table 1 on the poster. We have a few hypotheses about the source of error between the temperature values. When we created our thermal prototype, we tried to make sure that the resistor was placed in the middle of the conduit to create a more even temperature distribution. And we assumed that the resistors were in the middle of the conduit and placed the thermocouples in the middle as well. But it's possible that the resistors were not directly in the middle, which would create a more uneven temperature distribution, which then introduced error in the temperature readings. In the case of thermocouple 1, we hypothesized that its location among the cells is what created significant error. If you look at figure 4, you can see that thermocouple 1 is in the wake, and we predict turbulent flow based on the velocity of air from the fan, the thermophysical properties of air around the temperatures that are shown in the CFD, and the spacing of the batteries. When flow is turbulent, large temperature gradients between the surface and the surrounding fluid form, and the temperature gradients make it much more difficult to accurately measure the temperature within the wake. So it's possible that the temperature readings from the thermocouple is not accurate, and that would explain the significant error between the temperature readings.
Okay, so the two outputs of interest from our FEA models are maximum displacement and max Mises stresses. The stresses in the container can show where increasing or decreasing the amount of material is possible to optimize weight. Maximum displacements can show that the container and the segments are safely contained within the vehicle chassis. Max stresses, displacements, and the locations of the maximum displacements for the 4 simulations are shown in the table 2. The displacements at the end of the forward simulation are shown in figure 5, and the max stresses found in the forward simulation are shown in figure 7. If we look at the forward simulation as an example, we found that the max stress in the container reached 616 MPa around the mounting holes in the base flange, briefly rising above the maximum tensile strength of the steel of 515 MPa before receding. The rotation of the container around the side-to-side center line of the base panel causes a maximum displacement at the top of the container of 14 millimeters.
Okay, so kind of just an overview on our CFD results throughout these last 2 semesters. After we validated our CFD simulation, we changed the geometry to match the actual segments within the accumulator container. Reran the CFD, and basically what we got was two main results. So the first being that the optimized spacing between each cell is 21.5 millimeters. This gives a more compact spacing and better ergonomics for the container fit. The second goal that we realized was the surface temperature of each cell was below 60 degrees Celsius, which is exactly what we were aiming for in our designs, in our design metrics. So overall, we believe we've characterized this container pretty well as far as thermal capacity and thermal capabilities goes, for as far as a air forced convection cooling system goes. So.
And the goal of the FEA model is to show that the container meets strength requirements set forth by the FSAE rulebook and show that the container and accumulator segments are contained inside the chassis of the vehicle in the event of a high-speed impact. Based on our results shown in Table 2, we predict that the container will stay rigidly mounted to the chassis and safely contain the batteries in the event of an impact.
So the final deliverable of our project used to be a fully manufactured and assembled container on design day, but due to the COVID-19 pandemic, that's no longer an option. So we switched our deliverable from a manufactured container to a set of manufacturing work instructions that we've written up and have given to the FSAE team so that they can manufacture this container on a later date. So included in those instructions are the contact information for the different professionals and companies who we were outsourcing various manufacturing steps to, the list of materials, contact information for the team members in case they have any questions. All of our information is there and they can reach out to us. And then it shows just the order to complete steps in, where to find materials that we've already purchased for this container. And it's just a complete step-by-step instructions for how to manufacture this thing. What we've also included in that are also steps for editing the FEA and CFD models. So if they make some minor design changes in the coming months to their segment, they'll probably have to change the container CAD model. And then if they need to rerun this, we have instructions for how to edit the FEA. The other benefit of having like instructions for how to edit the FEA and CFD are if in the coming years the team decides to drastically change the geometry of the container and they want to rerun any of kind of simulation, they can use our FEA and CFD as like a guide for how to rebuild a new one to match a different geometry. So overall, they do have work to do to manufacture this container in the future, but we've set them up pretty well so that they can move forward with either going straight to manufacturing or to make minor design changes if necessary. Move on to if you guys have any questions.